This talk is called Modified Condition Decision Coverage in GCC, and I think I'm contender for worst title of the conference. Unfortunately, there's no way to both to not use an acronym and at the same time get a reasonably sized title that also doesn't sound miserable. So I apologize. But we'll be talking primarily about modified condition decision coverage and its implementation in GCC. Who's ever heard of modified condition decision coverage before? Yes. Okay, so let me guess. Well, I mean, auto, medical, and auto, yeah. Right, figures. I've dubbed before modified condition decision coverage as one of the most overrated and at the same time most underused metrics for test suites. And maybe we'll see why. So we have a few topics that we'll go over. We'll go over just general code coverage for those not in the loop, brief overview and a taxonomy. We'll introduce modified condition decision coverage. This is probably the last time I'm going to say the full thing, and I'm going to keep it to MCDC, which is the acronym, which is almost as bad as the name itself. We'll look at some programs, and assuming we have the time, a thorough description of the algorithm that powers the implementation in GCC. There's a notation warning for that. If you were at the Maths is Fun talk or have some basic idea on set theory, this should be all right. If not, I apologize. By the end, I hope you will be familiar with line, branch, and condition coverage. You will know about different kinds of MCDC because there's more than one. You'll understand the mass conditions and be able to measure, of course, using the tool. And you'll have seen some cool maths. I've also woven in some nuggets, some words of wisdom that I'd like to share. My name is Jørgen. I work for Woven by Toyota, which, as the name implies, is a part of Toyota in Japan. Right, code coverage. Code coverage, sort of formally, is a collection of metrics that you run on your test suite, really. And it tests for it measures different properties. Typically, programs are instrumented to record some runtime information about what he has seen, which is sensitive to inputs, and results are typically aggregated across multiple runs because programs behave different under different inputs. So here's a nugget already. A coverage metric should not be a goal unto itself, but a measurement of how well the requirement tests exercise the structure of the program. This is from a paper called A Practical Tutorial on MCDC by Hayhurst and some other people from NASA in 2001. This is unfortunately often lost because notice how the emphasis, by the way, is mine, but notice that they bring forward the requirement test first. You first design your requirements and the test that would verify those requirements, and only then do you measure how well that maps to the structure of your program. So let's do a silly example. So we have this function, which maybe records something. And as you can see, whenever it rounds up, then a counter is updated, and otherwise it's not. And you would assume that this should not round up when you give it 6, but it should round up when you give it 0.6, right? It's usually the more or less half. Of course, this program has a bug. If you can spot it, be very, very proud. He used the wrong comparison. But the problem is that it's very easy to write a test suite which does not pick up on this. And in fact, if you run gcov on this with these two inputs, you will see that on line 14, the return false is never exercised. It isn't used. That's not what you'd expected, right? If this was implemented correctly, you would have expected maybe around 6 to exercise the else block. So this is something, as an almost trivially stupid example, that would go through your test suite. Oh, sorry, it would pass your test suite, but you would still have a pretty pointless check, at least according to the tests. Okay, so we have 3 very popular coverage metrics. It's the line or statement coverage, It's the branch or decision coverage, that pretty much means the same thing, and the condition coverage. And you break them down into, answer of the question, has every line of the source been executed? Has every control flow structure been evaluated to both true and false? And if every Boolean sub-expression has been evaluated to both true and false for line, branch, and condition statement coverage, respectively. If you worked with coverage before, this is probably something you're familiar with. But I would point out that even line coverage can be a significant amount of effort to have full line coverage of your program in your test suite. So, okay, an example. Here we have the bad adder. And as you can see on the line was at 5, we have a dead statement, right? Because it's after the return. It's dead as a dodo. This program can obviously not achieve 100% line coverage, right? But depending on your test, this may or may not do what you want it to do, or it might test correctly. But anyway, coverage would certainly not be 100% from that. And then you wonder, why is there a line in your program that isn't touched? Is it because it's not actually used? Is it a condition that you haven't, or a path that you haven't done? Or is it, in this case, dead? And if it's dead, why is it there? Why is something dead in your program? The previous example is obviously silly because it's pass or return and the compiler would want, but you have other cases that very quickly can be interesting. So for instance, in this case, failing either of the preconditions doesn't give you a different return value to check against, so they're impossible to distinguish. So arguably in sort of TDD perspectives, this would be bad, or this would be a bad design choice in the first place, but there could be contracts, there could be other things. So libc famously, or syscalls, have a lot of failure conditions that they don't finally report. And then the question is, in your test suite, you test for bad preconditions, but did you actually get all the cases? What if the second precondition never evaluates to false? Why not? Could there be a bug in there? Is it just not sufficiently wide inputs? What other things do you have there? Interesting or important questions to ask. And then you have the branch coverage. And the branch coverage is satisfied when every control flow structure has been evaluated to both true and false. So in this case, you need to enter both the then and the else block for this to be the case. Okay? How is this different from statement coverage? Anyone have any immediate idea? It's a simple counterexample. No? Okay. If X is true here, this has 100% statement coverage, but only 50% decision coverage, right? Because you're evaluating every line, but you never actually see X being false. Had X been only false, then obviously you wouldn't have full line coverage either. So in the cases where you have both a then and an else block, statement and branch coverage will be the same thing. But in general, it's not. So when you have functions like this, which is accidentally always true, because there's actually a bug in always true, in that it returns always true, your test suite with plain line coverage would not detect that unless you were very sensitive to first happening, but first could be a side effect. It could be a print, right? So it might not be easy to pick up in your test suite either. Full disclaimer, most of the examples here are, slideware and trivial. So they test for behaviors that most test suites should be able to catch anyway, but they're for the illustration. Okay. So the requirement is that for every control flow structure, you have tested both the true and false outcome. For and while, for example, they are really ifs, but with beds on, as demonstrated in this program here, right? So you have the while condition and you with the body. And you have a loop label, a check of some condition, and a go to end loop. And at the end of the body, you go to the top of the loop. if you run this through GCC and GCOV, it will agree with you. See, it has the same pretty much behavior under the condition, and it looks very similar, right? So looking at just ifs is not sufficient. You also need to look at loops. Okay, so condition coverage extends this a bit further. And in order to satisfy condition coverage, you need to test that every Boolean sub-expression is evaluated to both true and false. So for this program here with, well, x and y, and these inputs, this is accumulated. Running both with false would give you a 25% because the y would be short-circuited. Running it with double false. With true and false, you would bump it up by 50% because now you would have seen x as true as well. And by finally passing it 1 and 1, all of the Boolean sub-expressions have been evaluated to both true and false, right? So far, this is pretty straightforward. So let's expand a bit on the statement and decision coverage. So let's assume you have this program where your loop condition is accidentally always true. It's perfectly easy to write a unit test suite for this, right? You just need to make sure that it breaks at some point. So the loop will always terminate under the assumption that G eventually turns true, right? It's perfectly possible for this to have 100% statement coverage, but not decision coverage. And so this is slide code, but there are subtle interactions, especially when you're dealing with third-party functions that could behave oddly that you need to cover and test for. Okay, so let's do more condition coverage. Instead of y, what if we have the accidentally true always function instead, right? So what we would like is to have these numbers here, 25, 75, and 100% coverage of these three inputs. But that's clearly not going to happen because you're never going to see y being false. And condition coverage is clearly insufficient to detect obvious failures. So if this code would be acceptable according to the requirements, why is y in there in the first place? Then it's obviously only dependent on x, right? It doesn't make sense. Okay. Running this through GCOV will show you the same thing. And then you have this gem. So anyone familiar with what's going on here? Yeah? So this is the rule of n. I assume 5 it won't stay at 5. And the problem is that it is pretty much required that move and copy assignment or construction doesn't, like they should be almost interchangeable in the sense that it shouldn't change the semantics of the program, right? But assuming these are written by hand because they do something non-trivial, they have to do different work depending on it being a move or copy. And you can have a perfectly fine and wide test suite, but at the end of it, does it actually call the move constructor or does it fall back to the copy and you can't tell the difference? This can very easily happen. And a good way to detect it, well, it would be coverage, right? I was at the talk with Tony, sorry. And he pointed out that C++ is the only language that he knew that lets you specify a custom copy and then proceed to do its best to never call it. You can have defined all of these, and because of return value optimization, never use any of them. This is a good way to at least verify that at least once this has happened and it did what it should. Sorry. Okay, so let's talk about GCC. GCC will emit GCNO files, which is briefly is just source annotation, and running the instrumented program will create and or update GCDA files, which is just counters. These will be in your file system. So the quick start with coverage in GCC is to build with double dash coverage and link with double dash coverage in case you slice your build. You run your program, your test suite with whatever inputs you find appropriate, and then you generate the report by running gcov and the program, or variations of gcov and the source file. And after that, you're very confused and you read a manual, hopefully. As a general advice, I would say that lcov, which is it's a visualizer, if you will, for the gcov output, is very useful. It brings you a pretty rich source annotation and some summaries. Results are really only reliable if you build without optimizations on. So this could bring some constraints to, or it could be impractical, especially in things like games. But in games, I'm not sure if you would do this anyway. And sometimes you want some optimizations on so that the right kind of elimination will kick in. There are reasons to build even test builds with optimizations. Particularly the source mapping is vulnerable to this. And just apply common sense and good engineering when working with these metrics. Okay, so let's move on to MCDC. I'm going to try and answer how it's different from condition coverage and why you should possibly care. So one reason to care is the lizard people, which are the regulators. Because if you're in the auto industry or the medical industry, it is very likely that you will have to go through some regulatory process for your software to be used on people. It's one thing to have your program crash. It's a little less fortunate to have your car crash. Right? So for safety critical software, as it's defined under the ISO 26262 and the DO 178B, the latter is for, I guess, former if you look at the list. So the DO is for aviation and the ISO 26262 is for the automotive. So that for the safety critical pieces of software, you need 100% MCDC coverage. But ignoring that, why actually care? Well, for one, I think it's actually a pretty good metric. There are some insights that you can draw from it that are very valuable, such as unintended data dependence in your program. There are some classes of bad expressions and bad logic that you can detect. It forces you to test more interactions and data paths in your program, and quite frankly, drives robustness. So the problem with decision coverage, if you recall, is you need to test that both true and false are seen from an expression, is that here we have 3 variables in it, right? We have, what's that mean? No, okay. We have the A, B, and C, right? And you now only need 2 tests to cover that. So you have 2 tests for 3 variables, right? It's a pretty weak input. And clearly there are interactions here that can't be captured with 2 tests. So MCDC is satisfied if formally every entry and exit point has been invoked, every basic condition has taken all the possible outcomes, and each basic condition, as so to speak your variables, have been shown to independently affect the outcome. This is a bit of a mouthful, I know. We'll try and break it down. So every entry and exit point has been invoked. This is branch coverage. Right? Sorry, this is decision coverage. My apologies. Right? So do you go into the then and do you go into the else? That's it. Oh yeah, okay, so in the proper sense of branch coverage, it's correct. Okay, so every basic condition, oh yeah, so in the table here, this is the truth table for this expression. I've highlighted the rows that would be sufficient in order to comply with this, or to satisfy the requirement, right? Okay, so you also need to make sure that every basic condition has taken on all the possible outcomes. That is, A is seen as both true and false, B is seen as true and false, and C is seen as true and false. And by looking at the truth table, if you give it these three inputs, you can see A has F on the top and then a T. B has an F on the top and then, actually on row 6-2, and a T. And the same goes for C, right? And then finally, each basic condition has been shown to independently affect the outcome. For this, you need 4 tests. I'm not going to go into the why just yet. Okay, so what motivates this? Well, you can, of course, test the power set of inputs, right? The 2 power to n inputs. But it will not actually reliably catch any more defects than you will catch with MCDC, at least not when it pertains to logic. In general, n+1 test cases is sufficient for coverage, but please bear in mind that n+1 inputs might not be sufficient for actual good testing. It's different. So the problem with MCD, the way I see it, is that it primarily tests the implementation and not the specification. So if your algorithm is terrible, it doesn't matter that you have coverage. It's possible to cheat. We're going to look into what that means later. But it is possible to reduce the requirement of the test suite by slightly editing your program. In practice, you might need, in order to fully satisfy coverage, many test cases that aren't all that interesting. And a good example, I try to think of what is a good example where you don't really necessarily want all kinds of interactions tested, and command line parsing. Like deep interactions in that is probably not going to be so interesting. It's awful to determine without tooling. Doing this by hand for any expression larger than 3 is just miserable. It can be very expensive in engineering time because you need to write all these tests, and especially deep into functions, it can be difficult to synthesize the right input in order to get there. And it can also be at odds with fuzzing. And what I think is the most damning is that it can lead to what I call metric-driven development. It's where you primarily design your program around satisfying the metric and not writing a good program. So I have a couple of nuggets from the SQLite people. From their testing page, SQLite is probably, if not the most, then it's certainly up there, most well-tested pieces of software in history. It is absurdly well-tested. And SQLite goes into fighter jets, so it has to comply with aerospace regulation, which means that they need MCDC, right? And what they write on their page is that because MCDC testing discourages defensive code with unreachable branches, because of course unreachable branches would not satisfy the requirements of MCDC. But with defensive code, a fuzzer is more likely to find a path that causes problems. And MCDC testing seems to work very well for building code that is robust during normal use, but fuzz testing is good for building code that is robust against malicious attack. And malicious attack, if you're in something like a car, kind of sounds, oh yeah, but that's not going to happen because it's a closed system. But users are very good at acting maliciously, but not on purpose. So it can still happen that you give it all kinds of bonkers input. And even then, malicious attacks can certainly happen to vehicles. Okay, so we're extending this table, this taxonomy of metrics to include MCDC. So in order to satisfy it, you need to check that every control flow structure has been evaluated to both true and false, and verified that every condition has been shown to independently affect the decision outcome. Independently means that if you have a particular test input for your condition, for your expression, if you can change that one variable and flip it, the outcome would change. So if your expression is true because you passed it true, and one of the variables get turned to false, the expression should now be false. In that case, it does independently affect. That's what it means. Sorry. Okay, so we have a couple of types of MCDC. We're going to cover two of them. The first is the unique cause, which states that only one condition may change between a test vector pair, and the resulting decision must be different between the two. So here's an example of that. Okay, so assuming you have the expression A and B or C and D, you need to pick a set of inputs where changing one of the variables, and only one, in between, well, I guess the rows of the table that I put down for you there, while at the same time changing the outcome. So what you have, you can see in the rightmost column, that's the outcome of the expression. It goes 0, 1, 0, 1, 0, 1, right? And you can say, I've highlighted the change in between the rows, right? Or rather, what I've highlighted is the values that you now have coverage for, the inputs you now have coverage for, right? So in the first one, the only one you get is 0 on A. And then A and B for true, B and C for false, C and D for true, and D for false. You need n plus 1 tests in order to satisfy the unique cause MCDC. And if there are strongly connected strongly coupled conditions, which essentially means that you have the same, either you have the same variable or they somehow depend on each other, so that by changing one, then the other one will change as well. There is no coverage set, and this cannot be satisfied. So that's actually a strength. That means that if you have that, then obviously you probably did something wrong, because why does it go into the expression if it doesn't actually do anything? There is another kind, which is called masking MCDC, which states that only one condition having an influence to the outcome may change during a test vector pair. So this is an example of that, and you can see that the blue, the marking, is just all over the table now. So it doesn't follow this nice structure. But you can get away with much fewer test cases. So it's the double square root of inputs rounded up is the minimum test cases you need. And what this gives you is that you have more test vector sets to choose from, which is a benefit because you can more accurately map to the requirements tests that are natural to do, right? I've plotted the difference as the number of conditions go up. And this isn't so common anymore, but it used to be the case, and especially in aerospace engineering, that some conditions, it wouldn't be uncommon to have at least a few dozen, maybe 32 condition expressions. And doing this for 32 is just miserable, right? But then with masking, you can get away with, what's that, 11, 12 maybe? Tests and still pretty much have the same level of confidence. So it matters for really big conditions. They aren't so common anymore, but it can still happen. Note that for small n, n plus 1 and 2 times square n, root of n, is pretty much the same thing. Okay, so Chilensky states that masking MCDC generally requires fewer tests, but it is as good as at detecting errors. And he has a long analysis of why. And if you can get away with fewer tests and still get the same thing, why wouldn't you, right? So from now on, we're going to focus on the masking MCDC. But yeah, so I wrote a patch for GCC. The juicy bit is about 1,000 lines long, and about a third of that, I think, is comments. To use it, you would, in addition to coverage, as we saw before, pass the profile conditions flag. It increases build time a little bit, but I think it's perfectly acceptable. And this is what it looks like when you do it. So you have a program A and B or C, you run it with 3 inputs and run gcov double-dash conditions on it, and it will tell you that this has covered 4 out of the 6 conditions, and it also tells you which ones that you haven't gotten. So the question is, why is A equals 1, which you can see is clearly passed on the 3rd line of input there, not covered? This section, the rest of the talk, covers masking MCDC. Not too much changes for, well, actually, I take back. Unique cause wouldn't have to deal with this, but this is the price you pay for a smaller input. Okay, so let's go back to the requirement. Is that every basic condition has been shown to independently affect the outcome, right? A condition independently affects the outcome if changing it while keeping the other values constant changes the outcome. This is shared with unique cause. So let's look at these 2 rows, yeah? In the first case, they're all false, and in the 3rd case, the A is true. So this is the input we had here, right? On line 1 and 3 on the input. And as you can see from the rightmost column, which is the outcome, the result doesn't change. It's still false, right, in both cases. So obviously A, being true, had no effect on this. This is what we're picking up on. So changing A does not change the decision while B and C are both false. And this effect is called masking. And it happens when the right side of an OR expression is true, and the right side of an OR expression is true, and the right side of an AND expression is false. So this takes a while to get used to, and we're going to try and build an intuition. Reversing a Boolean expression does not change its truth table, right? So A or B and B or A obviously always evaluates to the same thing. We're ignoring conveniently the fact that in C++ these things can have side effects, but from a logic perspective, this applies perfectly well, right? And the observation I made is that masked conditions are the conditions that would be short-circuited if you would just flip the expression, if you would reverse the expression, which helped me tremendously, build this intuition of why this is happening. So let's look at this. So in here, I have taken the same expression. The left table, I've starred the values that are short-circuited for those inputs. And in the rightmost table, I've dashed the ones that are short-circuited in the reversed expression, right? So because we're all used to working with short-circuiting, right? So whenever C is true in an OR expression on the right, then obviously it doesn't matter what B and A are, it's not going to affect the result. If we put this together, just note that I've, in the column table in the middle, I've changed the order to match the inputs, or the order of rows from the first expression and, the first table, right? So it's consistent with that. Okay. So the leftmost row is table is just the short-circuited ones, and in the second table you have the short-circuited in the reversed expressions, which are the masked ones. And what you get back, if you combine them, you get a table all the way on the right. And now you pretty much have a table that for this expression, you can see which values would actually be covered for that input, which is, I think, pretty great. So if you're doing this by hand, it's actually not a bad way to go about it and say, what test cases do you need, at least in order to ensure coverage? And you can just go over this list, right? So here I have this expression, and it's the same table on the left that you saw all the way on the right here. On the right here, I have the rows enumerated where the value is covered for true, false A, true, false B, etc. So I'm just highlighting here that in order to cover A, you can pick from these, 5 rows? 1, 2, 3, 5 rows. In order to cover B, you can pick from these 3. Or to cover C, you can pick from these 6. Putting it together, picking an intersection of these gives you, for instance, this one. But here, picking rows 7 or 8, either would have been fine. And this is what I mean that you can have different test sets. So let's look at the error detection that you can get from that. So that's masking, by the way. Reverse the expression, it would now be short-circuited. That's what's happening. Okay. So here I've just done the same thing. And note that the structure of this expression doesn't change even though C shows up twice, right? And what you can notice is that in the C column, the not C column, there is no F, right? This column here, no F. Which means that even if you gave this all the power set of inputs, there wouldn't be one where C was significantly false. I like that word, significantly false. So if you wrote this, the question is, why bring not C in there? Because it obviously isn't totally affecting what you're trying to do. It's probably a bug. The specification, remember, was A and B. You just typed it wrong. Just typing it wrong can, of course, happen, but imagine not C being the result of some other function that you thought should also return true sometimes, but doesn't for your inputs. Okay. Some strongly coupled conditions might not be detected by masking MCDC. So in this case, you can't have full unique cause coverage because A is repeated. But this particular example, if you run this through masking MCDC, you will still get the coverage you need. It's an accepted flaw. In practice, it doesn't matter very much for detecting errors, but it's something to be aware of. So let's move on to cheating. MCDC coverage in general is very sensitive to the structure of your program, okay? And one thing that you can do in MCDC, or in order to have an easier time complying, is that if you fold your Booleans, if you fold your conditions, they start, so when you fold them, you can have larger expressions really be output as a single condition. And when that is tested the next time, it doesn't actually reflect that it is being evaluated from a larger input set at all, right? So by rewriting the program on the left to the program on the right, which are obviously semantically equivalent, right? It's the same expression really, it's just that one does it in 2 steps. In order to achieve coverage, in the first case you need 4 tests, but in the latter case you only need 3, right? So this is perfectly possible. Proponents will say this is a good thing because it forces you to structure your program in an easier to read way, but I'm not so sure it's actually is a win. But it's certainly possible, and it's one of the drawbacks when dealing with this kind of coverage. So let's look at some programs. Some say that if computers had blood, we would be considered doctors. I think this applies just as much. If computers had blood, we would be considered butchers. Okay, so GCC does control flow graph analysis for coverage. What that means is that sometimes coverage can be a bit surprising because it's not actually instrumenting the source code, it's instrumenting the CFG. Semantically, these 2 programs are identical, right? And in fact, for GCC, it is, right? Both of these evaluate to be a single expression with 3 conditionals. This is sometimes surprising, but I would say that you have to expect that even at no optimization, your compiler will do a little bit of rewriting for you. And if you wrote the right-hand one and didn't mean to, why didn't you do the first one? Like, what are you doing? So in practice, this is not a big problem, but it can be surprising that it doesn't necessarily map one-to-one to what you thought you did. Okay. One cool thing about it being on the control flow graph is that it's front-end independent. So here's some Rust. It's very good Rust. So we have a program which is A or B and C, which we feed these two inputs. And if you run this through if you run this through GCC with the new GCC RS frontend, which is very experimental, so much that is incomplete and experimental compiler do not use in order for it to not just terminate. You can instrument Rust with condition coverage. And it looks like this, right? So this is pretty neat. I wrote this before the first Rust front-end patches were merged. And I just tried it and it worked. It's good when things are like that. It's not too often. Okay, so what do we have here? gcov reports the summary, which are the number of conditions that it found. In this case, it found 6 outcomes because each condition has a true and a false. So it's twice the number of terms. So it always reports a summary whenever it finds something. It reports on the condition index, and this is 0 indexed because we're programmers. This is sometimes surprising, but the source annotation facilities in gcov doesn't seem to preserve names very much. And this could also be the result of a evaluated function call, so it doesn't really have a name, and GCC treats them as indices, so that's just forwarded through. So that means you need to figure out where it's coming from in your source and do a 0, 1, 2, 3 in order to map it. If a condition is fully covered, it doesn't say anything because, I mean, it's quiet when you're doing it right, which I think is the way to go. So you can see A, in this case, has been seen as both true and false, and so nothing is reported for A, which would be condition 0. And finally, in the parens, it prints the conditions that it didn't see independently affect the outcome, so that you know where to look and try and figure out what's going on. Okay. Loops, while, if, are just ifs, but with beds, right? We already covered this. So we have this great program. I showed this to a coworker of mine who's deeply into Rust, and he said, yeah, this is awful. It is. It's there for demonstration purposes and to showcase the loop thing, not to be good Rust. We then discussed for a while and turned his computer into an almost brick by running a never terminating program. So joke's on him. Okay. So what do we have here? So we have one loop which is just while true, right? So no condition in the loop, but it does have a break. So it does a test and then it breaks, right? And we have a loop with a terminating, or with a loop condition, which is I less than 20, and I'm just making sure that it always terminates, right? So if you run this through GCC and then through gcov, oh yeah, and then we give it 0 and 5 as inputs. So you run it through GCC and gcov, and this is what pops out. So this is the other problem, I suppose, with this instrumenting the control flow graph, is that compilers are very happy to insert a lot of conditions you didn't explicitly put there. So on line 5, anyone have any idea what's going on? Come on. Wild stab in the dark. You could, if you would one-to-one translate this to C++, this wouldn't happen. That's a hint. Okay? Pop quiz. Rust conveniently checks for overflow on integers, which are reported because they're a part of the control flow graph, and GCC at this point doesn't know if it inserted it or you did. There is no real solution to this other than post-filtering, I think. Which means that it's pretty difficult to achieve full coverage on this, as you can imagine. The Rust C compiler, the LLVM one, will remove these checks on runtime. So you better hope that if you ever... you can't really rely on this check existing either way, but it could help you catch things in debug, assuming you have the test inputs for it. But okay, so on line 7, there is the if break, and you can see that both of its conditions are covered. And the same thing applies to line 9, which is the loop check. And you can see both goes into the loop body and out of the loop body, right? We saw earlier that this could have been an if and a label and go to, right? Which is really what's happening here. Right, let's look at some C++. I struggled a bit actually to come up with a good example that would show what I wanted to. But it works with pretty much any Boolean expression, including custom operators. Right? So this is not, all the other examples I've used so far have been on integers, but it works with anything that is a condition, including when you mix two different comparisons in a single expression. Running this through gconf gives you this. And I have to admit, I was a bit annoyed, but at the end of the day, I got over it. So what's happened here is that it actually detects two conditions. One for the expression itself, and one for the if, okay? So it first folds the Boolean expression 1 less than 2 and 4 less than 3 before then comparing on that. This doesn't change what you would have to do to achieve coverage at all, right? So if you have a 100% coverage goal, you would have to do the exact same inputs. So that's why it's kind of okay. But you would wish that it would be smarter and jump directly on it. So yeah, GCC uses temporary for the if. It works with D. Because again, this is on the CFG, so it's front-end independent. I copied this program from the dlang.org website, and I just picked one of the sample ones they put there. The problem with the GDC front-end is that when I ran this through gconf, nothing was actually reported, as you can see. The actual report happened deep inside the string.d file, because there's some template thing that actually does the comparison that we care about, and there's a lot of inlining going on. So not all front ends are a suitable go is not usable with my patch at all, because it breaks all conditionals down to single terms and then false. All right, so let's look at C. This is actually the same example that we had with the operator overload, which really is a function call. But in C, it doesn't use the temporary. I think it is because in C++ there could be an exception there too, and that it inserts the branch anyway, even when exceptions are turned off, because it was no except. But you can pretty much see the same thing, right? It tells you that 1 out of the 4 are covered, and then 0 misses both, but condition 1 has seen false. More C. If you would fold yourself into a variable, you still get a report for it. So this is pretty neat. And here actually you see the same behavior that we saw with the C++ front end. It works for ternaries. Because ternaries are really just ifs and assignment. Interestingly, if you would return, or if your ternary would be 0:1, or is 1:0, sorry, Oh, I guess either, because it could invert it. The condition disappears because it now is essentially a cast instead. So it's a truncation. Okay. And finally, here you have an example from before with or a complex expression. What you would do in practice here is, this is fine for toy programs, but for code bases with thousands and thousands of lines, this probably does not scale. So you need to look at aggregates, right? So, but this is good for surgically looking at specific bits and pieces you care about. But something like LCOV here would go a long way. GCOV also outputs in JSON, which is more suited for machine reading and annotation. So I hope that there will be more tooling on the JSON going forward. So what's the current status? It's still pending review. So I don't know when or if it will be merged. But since GCC is open source, you can pull the patch and apply it yourself and build. Inferring conditions from the control flow graph is very accurate with respect to what the program is doing, but it's sometimes surprising because it could pick up on things that are not explicit in your source. Approach is very sensitive to front-end decisions, as we've already seen, and reports can be very unwieldy. So hopefully something like LCOV will pick this up. I have an idea on how. And currently there's no integration with build systems or testing frameworks. But to be fair, this has never been a good story for GCOV. All right. So we have about 40 minutes left, and I hope to blaze through the algorithm that powers this. There's a little bit of a notation warning. This is slightly math notations heavy, but the underlying maths are not very complicated. So, okay. If you have a program like the one on the left, the compiler will essentially translate it to something what you see on the right. You have a bunch of labels for the variables, and then depending on the value where you would jump to. This is sort of pseudo assembly in C on the right, okay? If you would do this with what, if you went to the Maths is Fun talk called dots and arrows, it will look like this, right? So this is the same description, right? So depending on the value of A, you either evaluate B or C, and depending on the value of those, you either go to false or true or C, I suppose. So anyone who are completely unfamiliar with control flow graphs? Everyone have done compiler courses? Okay, good. Well, then this should be easy. Briefly, the control flow graph is a directed graph where the nodes represent uninterruptible sequences of instructions. Edges are the paths to the next possible immutable or interruptible sequences, uninterruptible sequences. Edges are labeled either fall through, which is straight, true or false, or complex. Complex, for the most part, we don't care about. It's for exception handling and similar. And an edge is either fall through or conditional. They're mutually exclusive. Okay, so this problem is in, well, 3 phases. And the first is, first we need to infer what is actually our expressions, what are the decisions we need to make. So in this case, for this full control flow graph for the program, I've here highlighted the conditions. So this is the result we want. Given this graph, we want to figure out that the expression is A, B, and C. Okay? And the observation that powers it is very briefly phrased as this. I'm going to try and read it. So, okay? The successors of the nodes that form the expressions are all either in the expression itself or in the then or else block. That's what it says. But I'm going to use these labels or names going through. So B is a decision or a Boolean expression, really, okay? Whereas O of B is the outcome of that expression. So that's a separate set. The NB is the open neighborhood, and square B is the closed neighborhood. So the closed neighborhood is the open neighborhood plus the, in this case, B itself. Okay? Any questions on that? Because yes.
Is OB the same as N?
Yes. OB and NB are the same thing. And parens, yes. Yes, that is correct.
And is the first one, is that meant to be N parens or N?
No, that is meant to be. So, yeah, no, that's correct. So the successors of all of the nodes that form the expression are either in the expression or one of the outcomes, right? And what that means when you see it in code, which is probably more natural, is that once you go into the expression A and B or C, you either end up in the then block or in the else block. There are nowhere else to go. So you might evaluate C, you might not be, but if you don't evaluate C, it is because you can go straight to either then or the else block, right? So I've highlighted or colored here the two components. The light blue is well, B, the Boolean expression, right? And then the outcome is the true and false nodes. And together they form this closed neighborhood, right? The reason I'm using the word closed neighborhood is that gives us an algorithm for doing it. Okay. Another thing to note is that all of the edges within the Boolean expression, they have to be conditional, right? Because conditional edges are flagged in the graph. They're marked as such. And the successors of the last node, which is the one I've thickened the lines of, the successors of the last node, or sorry, of the last term in the expression, in this case it's C, will have to be the outcome, which isn't really that controversial. That means that when you're evaluating C, you either go to then or else. There's nowhere else you can go. You can't start evaluating the next term that doesn't exist, right? Pardon? No, this is equals. It's definitely equals. When you're evaluating C, there's no more terms for you to evaluate, so you have to reach one of the decisions. Yes. Yeah, so successor here is set.
Sure, but couldn't C just go to false, for example?
No, not if C is true. Then it will go to true. Right?
I guess in a situation where A and B implied that C was already false.
Does it? I don't.
It doesn't in this case, of course.
Oh, right. Yeah, so but this is from sort of a variable perspective. If your data has that, then ideally my algorithm will detect that your tests or that you have interdependencies in between your terms, in which case, of course, this wouldn't hold. But that's the error that I'm trying to detect, or one of the errors I'm able to detect. But that's right. If you have dependencies in between them, this wouldn't be the result, but the structure of the decision, or sorry, of the expression, which is sort of generalized, because the structure of the expression isn't about the variables, it's about the operators between them, right? So, but you're absolutely right. That might not be the case if you have bad data or interesting data, but we're all about the structure of the expression itself. But, yeah. Okay, so you can't go to or from the middle of this Boolean expression, right? You have one way in and you have one way out. It's really what it says. But that's good because those constraints we can work with. So the first step is, it's really a BFS, right? It's a breadth first search. Reachable by condition edge is what we're doing. So let's do that now. So we start at the top because it's the first node in our CFG. And then you see, okay, if I follow just condition edges, where do I go? Well, you can go to B. Okay, we mark that. Or we can go to C, because it's also a condition edge. Okay. Note that here, any nodes with two successors, because they're two, they have to be condition edges. If it's one, it's a fall through. It's a simplification for the presentation. If you look at B, which is still in our set, we can go to the true. But when you look at the true, you know that this is, an end because it doesn't have a condition going out of it. You can also go to C, but C is already in the set, so that's okay. C, well, from there you can reach true, but that terminates. And you can reach false, but that terminates, and we mark it. This is just a plain BFS. If you type it up, it looks like this. I'm not going to dwell too much on it, but if you want to review it, then I'm happy to share this with you. Okay, so about a more interesting example, which is A and B, and then in the then block, you have another condition, another expression. So let's do the same algorithm again, but now sped up quite a bit. From A, you can reach B and C, oh, sorry, B and R. From that step, you can reach C and E. But note that C also has, C is also a condition and can reach P and Q. But the problem is that A and B is a closed expression and C shouldn't be a part of it. So just doing a plain BFS will obviously catch too much. So what we do is that we still do this BFS, but we now we now break this into 2 bits. Okay, we have what's light blue is everything that is a condition, right? And then we have G prime, which is everything immediately adjacent to what is a condition. That is whatever the condition edges point to, that stops being conditions themselves. Gonna skip some of that. So what we're gonna notice is that there is no path from the condition in the then block to the else. That's our observation. And it makes sense, right? So when you have a closed expression, it should end up in either the then or the else. But here we have the case where there is no path from C to R. But B has a path to R, which is also a terminating thing, right? So something is obviously amiss. Like you can detect that something's wrong. Okay. So what you can notice is that if you look at the 2 outcome nodes, they should both share ancestor sets completely. And what that means is that if you're in the then or if you're in the else, you know that you have possibly evaluated all of the Boolean expression to get there, but nothing else. And it's the same conditions that goes into both cases, right? So let's look at what's actually the set of outcomes here, which is R and C, right? They both have B and C in common. But if you look at, there is no path from P that also includes R, for instance. And R can, if you go R and up, there is no C in there, right? That's what we're seeing here. So for A and B, the outcome is, or really for this expression for A and B, the outcomes are either the then block or the else block, right? Okay, so let's use that. First, we do the same, or rather, we look at the ancestors of Q, right? Remember, this is our set of adjacent C. This is our neighborhood. So you have your, so we start with Q. So its ancestors are CBA, right? And for P, they have the same ancestors. But R, which is also reachable through only condition edges, its ancestors are only B and A. Well, it turns out that if you just take the the intersection of these sets, you get the minimal expression they all have in common, which has to be the first uninterruptible sequence, which has to be the first expression, right? So in this case, that's R and C. It's pretty easy to implement once you realize that. So another problem is that in order for this to work, your search has to start at the leftmost term in the expression. this is actually very easy to solve as long as you process your control flow graph in depth first order. And whenever you have processed a node, you mark it. If the if the node is fall through, you just, okay, fine, this doesn't matter. If it's a conditional, you there do the breadth first search with ancestor filtering that we just saw, and you mark the expression. And if you find a node that has already been marked, then you can just continue. Okay, because that means that that's just another path into an expression. Yes?
Does this algorithm mean you have to have an else block?
No. You don't need an else block. I mean, there is always an else block, which is just, past. Or there is always an else outcome, if you will.
There's always an else outcome.
Or a false outcome. Yeah.
So there is always. So that would be inserted into the graph.
Well, I mean, okay, we saw that. No problem. So videos. We saw that in one of the programs, I think. Yeah, this doesn't have an else. This doesn't have an else. And it still gets instrumented perfectly fine.
Yes. But if you don't, so do you still have if you go back to the example, so if you didn't have an else in the...
This one here, yeah.
No, go forward to where we had the graph.
Oh, sorry, yes.
So if the C expression, if C else, whatever was below it, you didn't have an else statement, then you have A, B going to R, then B going to C, and R going to C. Would that still be considered one expression? Or would it be considered two expressions?
It would be two expressions, yes. Yeah.
Don't you need the else block to make it two expressions?
Well, so that would only apply if you had a condition immediately into the else as well, if I get it right.
So if you didn't, I'm saying if you didn't have an else block,
right?
And you had the condition straight afterwards.
Oh yeah, so that's what we saw earlier. Then GCC will essentially merge them. That's correct, because then that's essentially your expression anyway, right? Unless the inner expression also has an else block. So you remember that if was the same as yeah. But there are some expressions that it will merge together, yes. And it just isn't able to distinguish them. Okay, so this may lead to expressions being evaluated out of order, but who cares, right? That doesn't matter because it's all compile time and it still gets instrumented right. At a high level, putting it together, it looks like this. So this is almost a one-to-one translation from the implementation in GCC. First, you do a BFS and collect everything that's reachable by following only condition edges. If there's only one edge, if there's only one node in that set, it's a single-term condition and you're just done. You don't have to do anything. Otherwise, you go through the neighborhood of the collection of nodes that you got back and you do this ancestor filtering because you know that the intersection of all of the ancestors will be the topmost expression. So otherwise you could nest this condition in the top of then as deep as you'd like, and you would get more and more wrong results as you go. But the ancestor filtering stops because it is the topmost block. This of course only works if you start at the first, but you can do that by processing the graph depth first. This is the same implementation but in actual source code copied from GCC. So this I'm very happy with because you can read the set operations straight out of the C++. Okay, putting that together again over all expressions, it's the same thing but in a DFS. Okay, so now that we've been able to infer individual Boolean expressions from the CFG, we need to figure out how they interact with respect to masking. So remember that masking happens when the right-hand side of an operator is true and false if it's or and respectively. And one thing you can notice is that Boolean expressions are isomorphic, or graphs corresponding to Boolean expressions are isomorphic under the operator. And what that means is that the shape of the graph is the exact same, independent of the operator used, but you use different labels. And here's the proof. It's cartoon. Another proof is just De Morgan's laws. That's pretty much what they say. And what that means is that we don't actually need to understand what the operator is to figure this out. We only need to recognize the graph shape. So if you look at masking, when that happens in a CFG perspective, when a value is changed in the expression, that corresponds to taking the other edge out of that node. Yeah? And if we still end up in the same outcome, then there has been a masking, right? Because obviously that edge change didn't impact the result. So here's an example, right, for A or B. And if A is true, you just go straight to true. If A is true and B is true, you go straight to true. But if A is false and B is true, you also end up in true. So in this case, it didn't matter that A was false because you still ended up in true. It's being masked by the B being true. So this is the same thing that we just intuitively think of, but represented in CFGs. What that means is that masking only happens in nodes that has multiple predecessors. Because otherwise, how can you possibly end up in the same node from different paths, right? Multiple predecessors also means that there's a short-circuiting edge. And as the tables demonstrated earlier, masking and short-circuiting are very intimately connected. The good thing is that means that we know where we can start searching for masking relationships. Some almost repetitions from maths class. Boolean expressions are associative. And what that means is that we can rewrite them into a sort of alternating form by moving the parens about. And masking will propagate until the operator changes. We're going to see an example, I guess, here. So when D is true, it will mask C, but it will also mask B, right? But it won't mask A because the operator changes. So it will mask two variables out. It doesn't matter if B and C are false because the outcome of the parenthesized expression is still true if D is true. Sub-expressions can mask. If C here is false, that implies in short-circuiting that also B is false because this is an OR. And that means that the right-hand side of A and B or C is false, and that would mask A, right? So this effect can happen. An observation there is that the last term, I dubbed it S omega for last, can short-circuit in the super expression. So what I did is I took this, I did this on paper when I figured out the algorithm. If you rewrite expressions in this way, but also do it sort of in levels, you can see that this is the same expression, but every time you do an operator change and a parenthesized expression, you go down a level, right? So you would have alternating and or. So if C is true and H is true in this expression, then D would be short-circuited, I would be short-circuited, and you would jump up and propagate that value to the next J, right? Or to the next term. But only jump up one level. It's kind of a firewall. If D is true, yeah, C would be masked, and you would continue evaluating E. But if D is false, now all of these on the top will be skipped, right? Because it's short-circuited by the fact that you now have a false in a series of ANDs. You would also mask A and B, Okay. So this is what you pointed out earlier too, is that the outcome is, or I pointed it out, but with it being the neighborhood, the successors of the last term in an arbitrary sub-expression will be the outcome of the expression as a whole. So when you're evaluating a condition, you either short-circuit whatever you have to the right, or you evaluate the next operand, right? That's what you do. So either you short-circuit something or you just continue on going. And the implication for that is that if one edge is a short-circuiting edge, then the other edge must be a masking edge. Incoming edges. So given a pair of incoming edges, which one is masking and which is short-circuiting? There is an ordering, so that if you have two nodes, if you have two terms, and one is a left operand, then it should have a lower index in comparison. This is what we need. So that if you have two nodes, you can tell which one is to the left, so to speak, in the original expression. It turns out this is easy to solve with a topological sort. Right now you have this ordering. So now, given a pair of nodes, and the relationship between them is that n is smaller than, if you will, than m. And then you also have that the n node, the n term, will be the last term in that sub-expression. And you know that the outcome of the sub-expression will be the successor nodes of that n. And the implication from that is that the other edge will have to be the masking edge. Okay. This is just repetition, so that we're sort of establishing everything we've seen so far, is that all of the nodes in a Boolean expression are either in the expression or in the outcome. Right, sorry, all the successors of the nodes in a Boolean expression are either in the expression itself or one of the two outcomes. All of this applies to Boolean expressions, which means it obviously also applies to sub-expressions. Okay, so given a node with more, well, two or more predecessors, find the nodes that are masked when an edge is taken, or that edge is taken. There can be more than one. As you know, for any multi-term expression, that's very easy. You saw that with A and B or B and C, and D. If C is false, then obviously both A and B are masked, right? And the solution is to go over the Cartesian product of predecessors. Where, I mean, with the ordering. In this case, it's a three-term one because it's the simplest one that actually exhibits the behavior. So our outcome node here is F, right? It's the false, because it's the one with multiple incoming edges into it. So we just start with a pair of them. And we have an ordering, so we throw away everything just so we know that which one is which. This matters for implementation, but not for the maths. So you look at this pair, and you see obviously A is higher up in the graph than C. And you do the same thing for the pair B and C, and finally for A and B. So that's what this means, is that just process them in pairs till you have all of them. Okay. So I figured out a way to compute or to determine which one or which terms will now be affected. And it turns out it can be neatly described as a fixed point. So we want to find a fixed point where all of the successors of a node are in the set. So let's just do it because it's easier to, and we have very little time. Okay, so we're taking the true example, or sorry, true outcome, the then outcome, and we're looking at its predecessors. And you can see that C is the lower node or higher up node, if you will. So it is the short-circuiting one, and taking D to T T will mask something. Okay. So we start by looking at the successors of C and saying these two are the outcome nodes, right? And then you see, you take all of the edges from our set D and T, goes into there, right? And remove them. And then you see, okay, C is a part of that. Or rather, so what we're looking at now is that we're looking at all of the nodes that still has an edge going into this expression. Okay? C is definitely one, so remove B. Or rather, all of the edges from that still point into this set that you're accumulating. Whenever a node has all of its, well, both of its successors in this set, it will be masked. So you do this, and in this case, you can see that C has both D and T in its two outgoing edges, so it is included. B has both C and D in this case now, but A has, like F is not already marked, right? You can see. So this is where the algorithm terminates, because you can now repeat this as many times as you like. Like just go over the nodes and see which ones still have the two, both outcomes pointing into this subgraph. Yeah, there's no one left now. So we have the nodes that will be masked by this will now be C and B, because D and T are a part of the original set, which you should then subtract, because this is what happens when you're taking this edge here, D to T, right? This is what it looks like in pseudocode. It's a bit longer in C++. I won't cover instrumentation because we don't have time. But essentially what happens is that your program ends up looking like this. So for the expression A or B, you can say every time you do take a condition and you go into that block, you will accumulate, or so you will update a local accumulator, and whenever you go to an outcome of the full expression, you will flush those into global accumulators, which will then be written to the file. So in this case, these edges that I've thickened will flush the accumulators into the global ones. Right, thank you. We are almost out of time for questions, but we have 5 minutes if there are one. So I'm Jørgen. You can reach out to me on that email address if you'd like to. Here's the name of the resources that I used to build this. And I was graciously sent here by my employer, Volven by Toyota in Tokyo. Thank you.